Hi, so I'm Tomlinson. I'm Chief Technology Officer for MapArt Systems. We're an augmented reality company focusing mostly on non-destructive examination and testing. And for the first part, I'm going to hand it over to Keats.
So I'm Keats Webb. As was said, I'm a digital imaging specialist at the Museum Conservation Institute, which is a part of the Smithsonian. We're a center for specialized technical collection, research, and conservation for all the Smithsonian museums and units. So the work that I do, the scientific and computational imaging that I do, is for the support of conservation and research within MCI and also the Smithsonian. So the image data that I create ties in directly with the MapArt OpenSource Viewer that we're going to be showing you, and it's a layered solution for viewing scientific imagery. So documentation is very much a part of conservation and research. Imaging has been used as a non-destructive examination technique and tool for conservation. As stated in the American Institute for Conservation Guide to Digital Photography and Conservation Documentation, documentation is basic to the ethical practice of conservation. Conservators have an obligation to produce and maintain accurate, complete, and permanent records of examination, sampling, scientific investigation, and treatment, as stated in the AIC Code of Ethics and Guidelines for Practice. So basically, they need to create these records of what they're seeing and what they're doing. The purpose of this documentation includes establishing the condition of an object, aiding in the care and treatment of the object, and increasing the understanding of the object. And before going too much farther, I want to introduce the objects, and these are scientific images of the objects. So the first object is on the far left. It's an early 18th century typeset document, Italian typeset document, and it belongs to Jasun Sang. The middle object is an oil painting on canvas done around 1880 in Massachusetts. And it's about 16 by 20 inches. The typeset is 9 by 14 inches. And then the object on the far right is a daguerreotype. This is the negative image of the daguerreotype, and that's the earliest form of photography, which is around 1837. And this particular daguerreotype is about 2.5 inches, 3 inches. So as I stated earlier, I do scientific and computational imaging for conservation and research. And so these are using advanced imaging techniques to look at the objects in different ways. So different lighting setups, different wavelengths, different cameras. So the different techniques that I'm going to show you are some of the techniques that we use, but we also use a variety of other techniques. This is a very simplified electromagnetic spectrum, just to give you an idea of where visible light falls and the relationship with ultraviolet and infrared. The typeset document on the left is not truly in the UV, but it has that nice UV look. It's UV-induced visible fluorescence. So it's using a UV light source in order to get this image. The center is visible light imagery, and the far right is infrared going outside of the visible light range. So again, this is an early 18th century typeset document, Italian, so it's paper. It has a few different types of ink on it, and there's some handwriting. So a laser pointer, I've never used one of these. So this is vermilion, a red ink, and this is iron gall ink, and you'll see kind of how it changes throughout the imaging techniques. So UV radiation has been used as a conservation examination tool. With that said, this particular technique, reflected UVA, has seen limited applications in conservation. It's used a lot more in forensic, medical, and biological laboratories. And so UV extends from 10 to 400 nanometers, with UVA being the closest range to visible, from 320 to 400 about. And so UVA documents how the UV radiation is absorbed, reflected, and transmitted by materials. And this technique can be used for material characterization and differentiation based on that difference in the absorption, reflection, and transmission. So it can help with enhancing visibility of organic resins, gums, coatings, oils, varnishes, paint residues, and adhesives. And iron gall ink is a pretty good absorber of UV, so it can be enhanced using the UV light or a UV technique. This is UV-induced visible fluorescence. It's used much more widely within conservation. The UV energy is absorbed by the material temporarily and then re-emitted at a lower energy within the visible light region. And that helps with material identification and characterization. And so a lot of materials used in works of art fluoresce, including oils, gums and resins, many common adhesives, and some pigments and dyes. This is standard photography reflective visible light with a fairly even lighting. Pretty good standard documentation of the condition. This is transmitted visible, which with a paper document helps to look at the structure of the paper. You can see watermarks. In this case, you can see some of the losses, and the light's coming through the document. This is raking visible light. By having the light at an angle, it creates shadows that can emphasize the topography and texture of the object. So in this case, you can see some of the creases and some of the folds, but it can help with indentions, tool marks, lifting of paint or inlay. And similar to the raking light visible photography is reflectance transformation imaging, which is a computational imaging technique that also looks at the topography and texture of a document. And in this case, the color component has been removed and the surface is made to be much more reflective. So jumping into the infrared range, this is reflected infrared digital photography. It's using a modified digital camera. So it is near infrared. It goes from about 700 to 1100 nanometers, so beyond the visible. And IR has been used pretty routinely for conservation practices. For painting conservation, it can be used for the examination of underdrawings, detecting changes in composition, and visualizing obscured or faded inscriptions. So this is transmitted infrared digital photography using the same camera and same lighting, but the light is coming through the document. And the final technique that I'm going to share with you is false color infrared. And so it's an enhanced visualization using both an infrared image and a visible light image and using channel substitution. And it can help with differentiation and characterization of materials. So with acquisition of such a variety of image data, it creates a need to digitally layer this information in a way that's useful and accessible for conservators and researchers. So some current viewing options are to open each of the image files into different windows. So you can compare and contrast, you can zoom in and zoom out, but the magnification might be different between the windows. You might be looking at different areas of interest and then having to reopen and downsize as you compare the different images. Another option is to bring the images in as separate layers within a single document using an image processing software. This can be a great solution in that you can zoom and pan, you can change the order layer, you can change the opacity, you can turn the layers on and off. One of the issues is you end up with a pretty large file that is stuck to a proprietary software. So you're relying on your collaborators and the other researchers that you're working with to have a similar version of that image processing software and a machine that can handle the file that you're giving them. So in this case, this is a 400 megabyte file. It's 10 images that are 40 megabytes. Trying to get a single image from this to one of your researchers and collaborators is going to be difficult. The max file for a Gmail account is going to be around 25 megabytes, so you're stuck with this kind of tough situation. So that brings us to the MapArt OpenSource Viewer, which was created by MapArt Systems, and it addresses those shortcomings that we saw in some of the current options for viewing this image data. It uses Geographic Information System, GIS-based software to overlay the different image data in a dynamic and accessible way. And it allows researchers and conservators the ability to virtually walk through these objects in a multispectral and multidimensional way. So I'm going to jump out of the PowerPoint really quick. I'm going to run through some of the features. So right here you can zoom in and out. And I'm going to pan over so that we can look at that handwriting with the iron gall ink. The top layer is a reflected UVA image. Can turn that off and see the next layer, which is a UV-induced visible fluorescence. If I wanted to compare that one with this reflected infrared image, I'm going to drag that and just drop it off right under it and start to change the opacity. And you can see that transition, especially between that iron gall ink and the UV and as it fades into the IR. You can measure the distance of certain characteristics. And I'm going to, and you can measure the area. using a polygon tool. And Reed's going to talk to you a little bit more about the technical side of the software.
Okay, I'm going to get into the technical bits really quickly. This runs on a local server, so you can put this on your own machine and it'll run through an Apache server. You could also put it on a server at your institution, and then you can share these files between people in your institution by just sending a link. So instead of a 400 megabyte file, you have a link and it just loads all of this information from the server. So on that server, you're going to need, there we go. You're going to need something like Apache. The geospatial data abstraction libraries, which is a set of GIS toolkits. This is all built in Python, and so you need Python as well. PHP is what runs all the pages. And then finally, a lot of this relies on an OpenLayers library, which is, again, a GIS library that's JavaScript, but that's included when you download the open source package. Now, a lot of this is time dependent. What we end up doing is tiling all these images for different zoom levels, and so that process is very dependent on the machine that you're running. For the full-featured version, we obviously have machines that are tailored to this, but depending on your machine, it can take quite a bit of time. So what we end up doing is we get information about the image with GDAL info, which is one of the GDAL Python libraries, and then we tile the image like you see right here. Level 0 is a bounding box of 256 by 256 pixels, and then for each layer after that, you have 4 times as many images. So as a result, your resolution increases by 4 times every time you go down to a new level. So at about level 7, we reach a gigapixel image. All right, so we'll run through the different pages to process and kind of see what those are made of. So this is the upload page. It's where you start. In the top left, you can choose up to 10 different files, and it'll upload them and start to process them. The limitation here is that this is just a viewer. It doesn't rectify your images. You can't change the coloring. So your images have to be processed and rectified before you get to this step. If we look at it, this is a simple PHP page. It actually does have some JavaScript up there in the top left corner. Excuse me. So if you want to change some of these settings, you can see right now there's a limit of about 2 gigabytes on the upload. But you can change your PHP settings with php.ini is one of your customization files, and that'll change some of those behaviors. We list the current supported file types as PNG, JPEG, TIFF, and BMP. There are a lot of more obscure file formats that actually will work with this, and that's a very long list. You can see that in the documentation. Okay, I'm going to speed it up a little bit. In initiate.php, you'll see at the very top you can change the names of your layers to start out as file names, but you can make them something more descriptive, and then you put in measurements. So you've got width, height, and that drop-down bar is millimeters, inches, or feet, and that's for the measurement tool. So it's not just the painting. If there's a border around it, it's the measurement of the entire image. All of that output at the bottom is fed through Ajax, which is asynchronous JavaScript, and that's the process of tiling out all those images. So finally, we come to what we actually care about, which is this OpenLayers file that has all of the features in it that we mentioned previously. It's an HTML page with the OpenLayers JavaScript library, and then JavaScript and jQuery at the bottom for the controls. You'll notice at the bottom right where we've got those measurement tools, that tells you distance from the nearest corner based on the measurements that you put in earlier, and that's a custom part of OpenLayers. Okay, the pop-out, when you pop the controls out to the side, like we saw previously, is actually its own separate page, but it's pretty much a copy of the code from before. Okay, let's take a look at the beginning of how you go through this process. Okay, so you're choosing your images that have already been processed and rectified. You can choose up to 10 at any point, and up to 2 gigabytes on this machine, but whatever you specify. Now this part alone, it's uploading. It's not just moving the files, it's putting them through your server and then putting them back on the hard disk. That can take a little bit of time, which is why we're going to time travel here. but that also allows you to load it to a server within your institution. And the same thing will happen here. We're going to change the layer names at the top, and then we're going to put in measurements. And you can see it's giving you the feedback on the whole process, how quickly it's tiling. So let's see if we can skip forward a bit. Okay, so I'm putting in 1200 by 1500 millimeters. And then after we time travel, that button that says processing right now, we'll just say continue. And then when you go, you'll be on the Open Layers page, and you can just save that link and spit it out.
So the MapArt OpenSource Viewer is a great option as a layered solution for researchers and conservators to view a variety of scientific and computational imaging data for multiple imaging techniques. It can be used for a variety of flat objects. You saw paper, paintings, daguerreotypes. And by integrating that image data together, it can help with the condition assessment, increasing the knowledge and understanding of the object, and also informing the treatment. In addition to those uses, it can be used for comparing before and after treatment imagery, and the potential of comparing multiple copies of a single object to see any changes within those copies. The image acquisition doesn't necessarily change with using the viewer, and the viewer creates an accessible tool to better utilize, view, and share the acquired data sets. And as I mentioned, it helps with the conservation goals of the condition assessment, informing treatment, and then increasing the understanding of the object. It is open source, and the nature of open source means that there will be some limitations and known issues, but there also is the continued development with the community.
So on the flip side, we have the open source version, which is a very simplified version of this full-featured product. Here you can annotate the image with those polygons. You can see in the top left, you've got notes that go with all those polygons. And so you can still switch between all the layers. We're working on PDF exports for this information. You can also rectify images. That big white button is an upload button, and then you can put in control points and have your image rectified automatically. Because we come from an augmented reality background, as soon as you upload your images, they can be tracked with augmented reality. So once you draw a polygon there, you can point an iPad or any smart device at that painting. It'll track off of the painting, and it'll make these same annotations. So that is perfect timing. Thank you.